Record this computer. All right. So how are you guys? I hope you had a really good week this week. And just remember that on Monday is a public holiday, so no classes on Monday. So we'll miss our class from 1 to 4 p.m. So hopefully we can make a good lecture today through the topic, which is principles of fluid. This is a really very good topic for us to cover. It's actually, I like this topic because it's actually is my area of my PhD, and as well where did I finish my qualification as well from AUT University. So one of my, if you are mechanical engineering, you may be interested to check this textbook. Is one of my favorite textbooks in applied fluid mechanics. This is really good if you are a mechanical engineer to have a copy of it. Make sure if you want to get a copy is SI units. You don't need to get this textbook if you are a civil engineer or another engineer. Well, if you are a mechanical and you're interested in collecting ebooks or books, this is really a very recommended book. But for your course, you don't need this book. You don't need it at all. It's not just required. All right, so if we start talking about fluid mechanics, especially the topic we will be covering in this subject, we have many different applications for fluid mechanics. Just let me zoom and so you can get and see this lecture notes in better quality. So first of all, the nature of fluids and the study of fluid mechanics, introduction of concepts. We will talk about it in details. We'll introduce the pressure and how can we work in SI units, as we always talk about that. And as well, we will define density, specific weight, and specific gravity. I'm quite sure if you have done your study in your engineering fundamental or applied science, or even the last year NCA level 3 physics, you have seen these things. But today we may go in a bit detail in a couple of the topics if you have time. Otherwise, we'll see you on next session, which will be on Monday, not this Monday, the Monday after, because the next Friday you will have the project. So you may see the first thing we can talk about fluid is our blood flow and the heart, which is kind of like the pump for our system, which is trying to pump the blood to the arteries, which goes to the rest of our body and trying to give us a very nice blood flow. And other ones, you can see it in engines and cars, and also in the big pipes, if you're transferring fluid, liquids, gas, or air. So different types of fluids you can get. And from your lecture notes, if you can see the 3 common states of matter are solid, liquids, and gases. So technically in this topic, we will definitely consider the liquid and we will not do much of gases in this topic, but definitely if you are a mechanical or mechatronics engineer, you take this course in detail and you cover a lot of concepts of it. So let's start with the first definition. Pressure, we have defined this properties or parameter. Pressure is defined as the amount of force extracted on a unit area of substance or on a surface. So remember always pressure is equal force divided by area. And here is very important to say it's the force acting perpendicular on the cross-sectional area. This is very, very, very important to recognize that. So you need that cross-sectional area and where the force is acting perpendicular on it, so you can do it. So for example, if you have a cylindrical shape, your cross-sectional area will be pi over 4 d squared or pi r squared. Depends if you're using the diameter or you're using the radius. Liquids and gases. Fluids can be either liquids or gases. Definitely we're not talking about solids. And the following general descriptions of liquids and gases that we'll use in this course. So gases are radially compressible. It can be compressed, like for example, pneumatic systems. And liquids are only slightly compressible. So I'm quite sure if you have done some experiments in your physics class when you're trying to compress water in a bottle and assume it is kind of a rocket, and you see it will not go further if you compress it with compressed air, you see the distance will go, this rocket is very higher. So that kind of gases are better to compress compared to liquids, because the liquids can exceed the boundary layers of the surrounding. If it was a bottle of something. Imagine you have a can of or of a Coca-Cola and you try to push more water in it. You see by time it will be damaged. So again, another parameters we need to define the weight and mass, and what's the difference between both of them. So the first thing is the mass is the property of body of a fluid that is measured of its inertia or resistance to change in motion. And you know the units to calculate the mass is always kgs, and you need to be very careful to distinguish between mass and weight, because mass is measure of the quantity of the fluid. Now, what's the weight? Weight is the amount of that a body of a fluid weight, that is the force with which the fluid is attracted toward the earth by gravitation. And that's why what we did in mechanics, when you have any object, you find like we allocate the centroid of that object, and that's where will be the weight going downwards, and against that we have the normal force to it. So the units for mass we say is kgs, and the units of the weight is in newtons, which is a force going downwards, always toward the earth or gravitational. And the equation for the weight is equals to what? The mass times the gravity acceleration. And this is really something we have covered in the past, so nothing is new so far. Now, there's something we try to introduce as well here is fluid properties. Other fluid properties, such as we have the specific weight, we'll talk about it very soon, the density of the fluid. So, for example, you may get the density of water. It's completely different from the density of oil. And that's very important for us to distinguish different types of densities. Specific gravity, which we'll see what's the units for this specific gravity. The question mark, does specific gravity has units or is dimensionless? We'll see that. And as well, we'll talk about surface tension and viscosity, which is one of the most important properties. So if we start first thinking about or reminding you about SI units, the system we use here, please remember in engineering mechanics course, we always use the length in meters, times in seconds, mass in kgs, and force in newtons. So if in case they give you the time in hours, or 1 hour, so you need to divide that 1 hour by 60 like minutes, and that's 60 minutes, you convert it to seconds. So always try. It's the same thing for the length. If they're giving it to you in kilometers, you need to convert the kilometers length into meters. So that's how it works, the equations. So an equivalent unit for force indicated above is derived from the relationship between force and mass. F is equal the mass times the acceleration, which the units for acceleration, as you know, is meters per second square from the linear equations or motion application you covered in your test too. So here is just showing you how do we get the newtons. So the other way we could express the newtons unit is kgs coming from the mass and acceleration, which is meters per second square, which will result for you the unit Newton or the theory of Newton you describe it. So it's kind of rearranging the equation for that. Now this is again, I'll just remind you again what we discussed before. If it's 10 to the power 9, we call it giga, and if it's 10 to the power 6, we call it mega. So you have, for example, megapascal in the pressure, kilo 10 to the power 3, milli is 10 to the power minus 3, micro is 10 to the power minus 6, and nano is 10 to the power minus 9. So again, we try to just remind you about sometimes when you find the answer is so big, so it's better to divide it by 1,000. So if I had, for example, 12,000 Pascal, it's very easy to say it's 12 kilopascal. It's very easy. It's more recommended, and something we remind you about from time to time. I like this table. This is a very good table. It's showing you all the definitions in very shortcut for some of the parameters or quantities. So the length is meters, and sometimes we can get in millimeters or kilometers. Time is in seconds, but sometimes we get it in hour or minutes. Mass is a quantity of a substance in kgs, or also I show you, which is Newton second square per divided by meters, if you take the reciprocal of what we found from the force. Force or weight is push or pull. So remember the force. You remember when we had an inclined plane and there is an object going upwards. So this could be a force trying to push the object to go upwards, or pulling it down, or the opposite direction object. Always measures in newtons, which is kgs, meters per second square. You don't need to memorize these things because this is worked out by the equation. So how do I know that? We know force is equal ma. M is represent the mass in kgs, and acceleration is meters per second square, or we know by default force is in newtons. Pressures, what's the pressure? It's always the force divided by the cross-sectional area. Pressure is measured in Pascal or newtons divided by meter square. And as well, sometimes we use bar. We introduce you to bar and kilopascal. Energy, force times distance. This is a good revision what we had done last week. Newtons times meters, or joules, or the other derivation of it. Power is energy divided by time, so newtons times meters divided by second, or joules per second, which we call it watts, or kilowatts, we may get the answer. Volume, it's depends on the shape. So if you have a cylinder, if you have a cubic, if you have a rectangular, it's meter cubic, or sometimes you get the volume in liters. And we need to know how to convert liters to meter cubic. Area, so the area is also depends on the shape of the geometry. So you can get circle, half circle, and we provide you in the formula sheet for these different types of area. What I want you to do, guys, when we meet on the class, remind me so I can post the formula sheet for the exam, and this will give you an indication which equations you need to use, or what will be in the formula sheet. So kind of to save you time to be a bit familiar with the formula sheet. Now, what else? We have volume flow rates. This is something we needed a lot in fluid mechanics, which is the meters cubic per second, or liters per second, or liters per minute, or meters cubic per hour. It means the amount of volume of fluid is passing through the pipe or through the pump. This could be also the weight flow rate, which is weight divided by time, newtons per second, or the mass flow rate if it's mass per time, kgs per second. And there is a relationship between them, which we'll see later. Also, we introduce specific weight is the weight divided by volume. So that will be newtons per meters cubic. And the last one is the density of the fluid, which is the relationship between the mass of the fluid divided by the volume of the fluid, which is kgs per meter cubic. And you need to remember that step. So this is a very nice table. It summarizes what the things you need to know for solving some problems in fluid mechanics. And definitely what we're trying to say, sometimes you need to remember algebraic equations. I will take a bit break because I see the attendance is increasing, which is very good. So I got Ninant and Ranjit, and who is here? Taish and Sagar, Ranjit, and Michael, Matthew. Hida is here. Good. Diran is here. Diane is here. Number 14. Diane. And myself. Alan. Buddy. So we have 18. Okay. Please let me know, could we have this presentation on Moodle? Of course, I'll share this presentation with Moodle. I will put it after the class, definitely. I'll do that. Please, what I want you to do is to, on the chat, send your name. You can use it privately. So when I finish the class, I can take your attendance. So please just say, hello, my name is this. If you're using different username, just say, hello, my name is this. And what will be tricky things? Put your student ID, so no one will be taking your identity. And then later, at the end of the class, I will talk to you when we display the camera. All right. Yes, definitely. I'll put this PowerPoint slides into Moodle. This is actually my PowerPoint slides when I teach fluid mechanics. All right. So again, pressure is the amount of force extracted on a unit area of substance. My definition for it is always, I say it in this way, is actually the amount of force perpendicular on the cross-sectional area of that geometry you're trying to do it. So if it was a square, you take the area for the square. If it was a cylinder, you take pi over 4 d square or pi r square. So consider the pressure in the following fluids: glass of water, water in your piping system at home, nitrogen gas sitting in the cylinder. So we have different types of water going in under pressure. One of the most important things which people complain, it's when you want to have a shower in the morning and people say, hey, there's not enough pressure in the water heat cylinder. And that's one of the application actually people find like, oh, I'm not getting that enough pressure in the water. So that's where it's coming from. So two important principles about pressure described by Blaise Pascal, one of the old 17th century scientists, which he developed the Pascal formula, which is really good, help us to do a lot of application using hydraulics. Remember the same thing, I will give you the hydraulic system when you go and try to fix your car at the workshop. You find there is a hydraulic system to lift this car, whatever is the weight of it, is using Pascal principles, relying on changing from a small volume of fluid, pushing a big volume of fluid so it can lift the weight of the car. We'll see something similar to that under Moodle. And one thing we need to identify here, pressure acts uniformly in all directions on a small volume of fluid. This is very important. And in a fluid confined by solid boundaries, pressure acts perpendicular to the boundaries. That's the one always I was saying to you guys, it must act perpendicular to the boundary. So if we take this example, I will give you time to work on it. So water in a glass has the same pressure as the air above. It's atmospheric pressure on the top. Water in the piping system at home has a higher pressure than atmospheric pressure, of course, because it's a closed system. So as to deliver a reasonable flow from taps and your shower, especially if you are second floor or third floor. Nitrogen gas in a tank is held at very high pressure so that a large amount of gas can be stored at relatively small volume or volumes. So we have many different applications, but we want to see something really relevant to what we can do in some of the applications. Let's see this example. What I want you to do, guys, I will read the question for you guys. I will give you about maybe 5 minutes or less to solve. So the figure below, this figure, shows a container of liquid with a movable piston. So that's is the piston, the one here, supporting a load. Calculate or compute the magnitude of the pressure in the liquid under the piston if the total weight of the piston and the load is 500 newtons and the area of the piston is 2,500 millimeters square. So basically, what's telling you this, that's the total weight of the piston and the load is all 500 newtons. So the combined or the net weight of this one and the piston is equal to 500 newtons. Where is applying? It's trying to apply a pressure against the fluid. And we have the cross-sectional area for the piston, which is surrounding area covering that, is 2,500 millimeters squared. So can you guys write me down what's the answer? I'll give you time to work on it while I'm still taking attendance. Yeah. It's very basic question. Okay. We have about 18 people attending this session, which is a good number. All right, so have you done it? I'm starting getting some answers from a couple of you guys. So yes, the answer that's sent by Sagar. Yeah. Michael, I want the final answer in Pascal, Michael. Yeah, see, that's units. You need to do it. Parpinder, correct. And I missed someone early. Sagar Duran is correct. Yeah. All right. So let's show it to you. It's very easy to work this kind of questions. It's reasonable to assume that the entire surface of the fluid under the piston is sharing in the task of supporting the load. So we assume that the piston is pushing. Because if not really correct, the fluid will start leave or seal from the sides of the piston, and you don't want to do that. Therefore, it's very easy. Is to 500 newtons divided by 2,500, and that will give you 0.2 newtons per millimeter square. But that's not an acceptable answer, because we need to change the units to suit us. So if you convert that 0.2 times 10 to the power 6, it's just converting it. So instead of writing 200 kilopascal, which is another way you can do it, is to divide 200 by 1,000 and you make it 0.2 megapascal. Now, if you ask me which one is more acceptable, I prefer the answer to be in kilopascal. So if you say it's 200 kilopascal, it's really good and it's acceptable and no issues. All right, so this is the way how can you show it, but now I'm showing you the answer, how it looks like if it's 0.2 newtons per millimeter square, how it looks like 0.2 megapascal, and if it's in kilopascal, it's 200 megapascal. There is a guy just attending the class now. I got it. All right. So if let's see another applications about this very soon. There will be a couple of examples. Now, one thing when we study fluids, I said before, compressibility, and many of you will say, what does mean that? So it refers to change in volume. So when you try to compress something, it's mean if you have this amount of fluid and you try to compress it, you kind of make it look smaller. And this is kind of you creating an energy, internal energy inside the cylinder. So it refers to change in volume of a substance that's subject to change in pressure on it. So for example, if you have a bowl of water and you try to compress air inside, you're actually creating a lot of pressure inside and a lot of energy inside. And if you leave that ball, you find the energy from the compressed air will try to push the ball far distance. I think this is an experiment they do it at schools. Sometimes they use water, they try to compress water, or sometimes they use air, and then they can really launch this bottle of Diet Coke, for example, very high elevation or distance. The usual quantity used to measure this compressibility is the bulk modulus of elasticity, which we call bulk modulus, E. It's the change in the pressure or pressure differences divided by the change in the volume divided by the original volume. So what is happening, initial pressure minus the final pressure divided by initial volume, or final volume minus initial volume divided by original volume. These, you can find them, they are standard. So at atmospheric pressure and temperature, we call it room temperature, 20 degrees Celsius, you find the compressibility of water is about 2,179 megapascal. And for different fluids, for example, mercury is 24,750 megapascal. Why this is important for us? Because you can know how much is the fluid is compressible or not. Can you compress that fluid or not? So you see water and mercury, which one do you think? I want you now to think, which one is more compressible? Is it the water or the mercury? Michael, to convert a units to Pascal before is just, so it depends on the unit. So for example, you give me the answer 2.5 times 10 to the power 3 divided or multiplied. You need to go and find the difference between them. So the answer should be in kilopascal. So the best way, you had the 500 newtons, and then 2,500 millimeters you divide it by changing it to meters, and then you get the final answer for it. So that's the easy way for it. So which one you guys thinks is more compressible, water or mercury? You can Google that, don't mind. Or leave it till the end of the session. Ethyl alcohol is easily compressible between all the three. That's correct. Yes, that's correct. And mercury is more difficult to compress because the viscosity is different. Now, let's see another example. I will give you time to work on this example. Calculate or compute the change in pressure that must be applied to water to change its volume by 1%. This is a very, very easy example. I may need to give you some hints here because I think you haven't done these things. What does mean its volume changes volume by 1%? This is the delta V is changing the volume for it. But compute the change in pressure that's may be applied for water. So do we know what's the compressibility for water? Yes, we know it. It was just a standard given to us. The compressibility of water is 2,179 megapascal. Now, what is given here to us? Calculate the change in pressure. So we want to find the change in pressure. It's delta P. That's the change in pressure. That must be applied to water because we know the fluid changes volume by 1%. So I will give you time to see how can you guys solve this one. So the equation you need is this one. And the value for EV or compressibility for water is given here. And you have the change of the volume is 1%. So think how can you find it? And then the volume from all this application to find the change in pressure. I couldn't see any answers for this question. Any idea? I got an answer. Is it 2.179 times 10 to the power 10? Okay. We'll see it very soon. I'll just give the rest of you guys. This is just an application. It's just something basically from physics to remind you what you have done in physics in the past. The guys who just attending the class now, please can you write me that your name and student ID? They just who joined me in the last 2 minutes. There are 2 guys just joined in the last 2 minutes or 1. You just write your name and student ID. All right. So I got another answer, or possible -2. Okay, let's see. Let's see the answer for this one. So the 1% volume change indicates that delta V over V is equal -0.01. We saw in an earlier slide that the compressibility for the water is 2,179. So you're technically rearranging the equation. So make the delta P, the change in the pressure outside, and you just multiply the change of that volume by the initial volume times the compressibility. When you do that, you will get the answer 21.79 megapascal. I think the answer I got from Sagar, it's correct. And who was else that right? Matthew. Matthew was answers a bit close, but it's better to write, guys, in the units. Remember, when we're trying to find the pressure, it's always recommended to write the units for that application for it. So I doing. So what we're doing here, these standards is just to show you what are the compressibility of the water as a standard. You can find them even from Wikipedia. And then the tricky things about this question, that water changes volume by 1%, so kind of the reduction is a negative. So 1% divided by 100 is 0.01 and is a negative. So a negative number by the original of the equation minus that number times minus that number, you get 21.79, which is megapascal. This is just something related to that. I don't want you to go into too much detail in it. Good question from Michael. Why it's negative? I like that question. Why do you think it's negative? That's a very, very good question. What's the reason this is negative equation? Why the pressure change is negative? Any idea? I'm waiting for a response. Guys, any idea why this one is negative? So if we read the definition for compressibility, it refers to the change in volume of substance that is subject to a change in pressure on it. So the final pressure is greater than the initial pressure possible. Perfect. So what you're trying to do, so the final pressure will be bigger than the initial pressure, and then delta P, if you make it as a negative, that will balance the equation. So there's another one. Hey, can you upload this video on Moodle later, because I'm getting kicked off from Zoom now, and then because of for internet things. Yes, no worry, Ninant. We'll make it on YouTube, and you can watch it anytime you want, and the slides will be there. So guys, I want you to go to try to find why is a negative sign here. There's a very good relationship between the negative and compressibility. So I will leave you guys to think about it, especially Michael. I want you as well to think about it, and then we discuss it. So there is also another definition for properties. Let's talk, for example, about density. Density is the amount of mass per unit volume of a substance. The Greek letter for density is rho. So rho is equal to what? The mass is in kgs, and divided by the volume. Volume is meter cubic. So the units for that is kgs per meter cubic. And always we have different values for densities for different fluids. So for example, the fluid is same for fluid, like water. It has different density values change with temperature at some stages. Now you say, how is this? So for example, if you freeze the water slightly, there's a fresh water has different density. There is a normal water has a density. There is a standard density we use for water is about 1,000, but I think for the fresh water is 950 kgs per meter cubic. So there is a slightly difference. The density for mercury is 13,600 kgs per meter cubic. The density for oil, for example, is 850 kgs per meter cubic. So every time you have a different fluid, you will have a different densities. Now there is another property. Specific weight is the amount of weight per unit volume of substance. The Greek letters for that is gamma. Gamma is equal what? Weight divided by volume. So its weight is measured in newtons. So the dimensions for that is newtons per meters cubic. Or sometimes what they can do it is in liters, because liters is another terms of units for the volume. So if you write here down the density, for example, you know it's equal m divided by v, and gamma is equal weight divided by v. Now, if you look carefully, what's the common between them? If you try to rearrange the equation, v is equal to what? M divided by rho, and the other one will be v is equal W divided by gamma. If you make them equal, W divided by gamma is equal mass divided by density, or rho, and then you can find the new terms between them. There's a relationship between the weight and specific weight and mass and density. With taking into consideration the volume is constant between the same fluid. So if it's the same fluid. So specific weight could come as well in different definitions. So we have a specific weight, and now we have a specific gravity. Specific gravity can define in two different ways. The first definition for it, specific gravity is the ratio of density of substance to density of pure water at 4 degrees Celsius, which is 1,000 kgs per meter cubic. Now, if you look carefully for specific gravity is the ratio of the specific weight of substance to the specific weight of pure water at 4 degrees Celsius. So what's the difference between specific gravity and specific gravity? Both of them here, if you see there is a typo error, they have the same definition. One's supposed to be specific weight, and the other one is specific gravity. The definition between them is just God. So this one, it should be specific weight is the ratio of the specific weight of substance or the specific weight of pure water, or the other definition for it. So, in other ways, how can I rewrite these equations in two different ways? Either, see this equation here, specific gravity is equal what? Either specific weight of the substance, what do we mean that? Means a fluid we don't know, divided by the specific weight of water at 4 degrees Celsius, which is equals to the density of substance, which we don't know, divided by the density of water at 4 degrees Celsius. So I will exit from this slide and open new slide to show you how can we work on this one. I will just copy this equation so I can put it in the next slide, and here. All right. So this is a very equations. We give these equations in any application we try to solve or we try to determine. So, for example, let's give you an example. Specific gravity is equals to 0.8. Can you find the density of the fluid? So if I told you the specific gravity is equal to 0.8, can you find the density of the fluid? So for that fluid, which is specific gravity for it, is 0.8. So can you find it? So how can we find it? I'll show you step by step. So because it's giving to us specific gravity for that way, there are two ways to use this equation. I'll type another equation to show you the difference between them. So I can write specific gravity equals, I'll use the equations editor. And here, either I write gamma for that substance and repeating what they done. So where is gamma? Here. And gamma for substance. In this case, we don't know the fluid, but what we know, gamma for water. Gamma for water is equal to what? Do you know what's gamma? Gamma is equal rho G. Are you okay with that? Can we use rho G? Is that a relationship between them? Specific weight for it is density times gravity. I've seen one of the guys written that, which is correct. So I need to get rho times gravity acceleration. Let's use something from equations editors. So because gamma, put something here. Gamma, which represents for me specific weight, is equals to what? Rho, which is the density, multiplied by the gravity acceleration. Another way to define the specific weight. So if I have that, what's mean for me? The gravity acceleration is a constant number. So I will zoom in so you can see it better. So that's a constant number. So we could rewrite this in another way to show that it's not really, it's very easy to write it in different formats. So to have it, for example, in this way, we say it's also is equals to what? I open brackets, but before that, I'll make sure to use this one. So, open brackets, and then we put density for that fluid, let's say we don't know yet, multiplied by gravity acceleration, which is a constant number, all of that for that substance, the density for the fluid. Instead of S, we can write F, fluid we call it. Divided by what? Divided by 1000, which is the density of water, multiplied by what? By gravity acceleration. Now, if you look carefully here, what you can do actually, gravity acceleration from both sides, you just cancel it because it's the same value, is 9.81. So if I cancel this one with this one, what's left for you, if we continue in the equation, we'll write a new line, show you the difference between them. I know some of you start getting the answers, but I'm showing you guys step by step. So if we have the specific gravity 0.8, that's what's given to us, equals to what? The density of the substance, which we call it F at this stage, we don't know the fluid, divided by what? Divided by 1000, which is the density of the fluid. If we continue with that, rearranging the equation, 1000 times that, so will be the density of the fluid is equal to what? We'll do it step by step, is equals to 0.8 multiplied by 1000, and that will be equals to 800. Now, if you say 800 by itself, remember, I really like to see the units, so you can type kgs per meters cubic, and very easy, you can bring the meters cubic here, and that is the density. So these kind of values of density represent for me for oil. Usually I will zoom in here so to show you, and I'll explain in more information, more detail. So basically, when they give you for any density the specific gravity for it, it's very easy to use this equation. So two equations we're using here. Either specific weight, gamma, which gamma it represents density times gravity acceleration. So therefore, you can write it in terms of density of substance divided by density of water, which is a constant number 1000. Where was the gamma of the substance? The gamma of the substance is replaced by rho times gravity acceleration because it's replaced by the equation. So gamma is always equals to what? Equals density times gravity acceleration. Therefore, we replace it with that. and we call it, instead of S, I'm giving it F because I'm working represented with the fluid. Since they call it fluid, so I'm using the F from that fluid. That's just a naming things. You can still keep it S, but just I'm showing you. If they call this oil, for example, then I change it to be oil. Yeah, I'm recording this session. Hopefully all goes good. All right. So then you rearrange this equation again. So the density of the fluid, because I'm called fluid, depends on the information given to me. And remember, the gravity acceleration canceled from it. Therefore, what do I have? 1,000 multiplied by the specific gravity. That will give me the density of that fluid's rho F is equal 0.8 times 1,800. Remember, density is always what? Is kgs per meter cubic. If you forgot that, always remember the equation we say density equal what? Mass divided by volume. Mass is in kgs measured and the volume is in meter cubic. Now there is another trick here. Sometimes they give you the density in kgs per liters, because liters is another form to show you the volume, and you need to divide that number. Let's try another example. Let's give you this one. I will open another slide. So I'll just copy this one, and I will give you another. So this time I want you to work out and give you time for it. So let's say the specific gravity is given to you guys is 13.6. Can you find the density for that fluid? Give you time for it. Use the same principle we did. You can't find the density of that fluid. So specific gravity is given 13.6. Can you find the density of the fluid? Remember always to use the same formula we identified earlier and try to use it, and should be the same principles. I'll give you time and you can tell me what's the value for it. Good, Saga. Very good. Michael, well done. I will copy the last equation we used so I can just edit it. It will be very easy for us. So what's in this equation we change? The only thing we change is to write, instead of 0.8, we write 13.6, and here will be 13.6, and that will give you the answer which you guys are submitting, 13,600, which is density. Which density? Do you know which one? Yeah, Ronil, perfect. This is the density for which fluids? Can you comment? Which fluid do you think, guys? 13,600 kgs per meter cubic. Yeah, perfect. It's for mercury. Hello, Ibrahim. Please, the guys who are just showing now, write your name so I can take your attendance. Because later this chat, it's saved in my computer, so I can go back to it and I can tick you attending for the session. All right. So that's the way how we can calculate density. Depends if you have two definitions for specific gravity. As you remember, we say we could define it as the ratio of density of the substance to density of pure water. That's if you're using raw only. Or the other one is if you're using the ratio as a specific weight of substance, the specific weight of pure water at 4 degrees Celsius. So two ways of doing it. The only difference between them, it's multiplying by 9.81, which is the gravity acceleration. Remember always, at 4 degrees Celsius is a pure water, which has greatest density, 1,000 kgs per meter cubic. We did this example, and all good now. Now, there is something I was talking about it, which we moved on it. So the relationship between density and specific weight. Quite often, the specific weight of the substance must be found when its density is known, and the vice versa as well. The conversion from one to other can be made using the following equation, which we described earlier. gamma, specific weight, is equal what? The density for that fluid times the gravity acceleration, which is 9.81 meters per second squared. So always make sure to check for these equations, and that's what we did in the last slide. All right, so I have another examples for you guys, example 3 and 4. I will give you time. What I want you to do is to try these examples and submit the answers using the private mode. Write private for me, and I will check it with you. What's the units for gamma? That's a very good question. You guys, so what I want you to do is to write the equation for gamma. Gamma is weight divided by volume. So what's that mean? You remember the gamma, it's newtons divided by meters cubic. That's the units for gamma. Now, what's the units for specific gravity, guys? Specific gravity is a ratio, dimensionless, no dimensions, because you're dividing specific gravity with specific weight divided by specific weight, or density of substance divided by density of water. And that's mean always the units, they will cancel. So very good information that specific weight unit is newtons per meters cubic. Specific gravity is dimensionless, no dimensions for it. O'Neill, Allen, Buddy. If you got the answer, for example, 3, please submit the answer on privately. Use the private mode so I can see your progress. Don't forget unit, guys. Units are very important. In the exam, you miss units, you miss mark. So please always write the units. Make sure. If we're calculating a weight, you need to know what's the units for weight. If you're calculating for volume or density or specific weight, you need to know the units. Now, specific gravity, what we said, you need to know what's the specific gravity for that. Okay, I got only 2 answers from 2 students. Another one coming. Example 3. Example 4 will take a while. It's a bit of process. Yes, specific weight is gamma. So I'm getting an answer for the first one, 8,093.25 kilonewtons. So calculate the weight of reservoir of oil if it has the mass. So M is equal 825 kgs. So weight is equal specific gravity for oil. All right. So let's try the first one together. So the first question, or example 3, calculate the weight of the reservoir of oil if it has the mass of 8. So what's the information given to us? First of all, the fluid is oil, and the mass of that oil is 825. So what other information could help me to solve this one? So the weight times, so W, and then from W, you can convert that to be in a way. So if you look carefully, the weight is equal what? Mass times gravity acceleration. What that will be changing? That will give you 8,093 kgs meters per second. This is a big number. We say we don't like these big numbers, which is in newtons. Just you multiply the mass times the gravity acceleration, that's the weight of it. Because using what we did from the previous topics in mechanics. Now, dividing this by 1,000, just you convert it to kilonewtons. Many of you did manage to submit this question very good. Now, the example 4, which is related to example 3, if the reservoir from example problem 3 has the volume 0.917 meter cubic, calculate the density. So how can we calculate the density? If you know the volume, definitely you can calculate the density. Mass, 825, divided by the volume, 0.917 meters. That's exactly like kgs per meter cubic. So straightforward, you get 900 kgs per meters cubic. And I can see many of you got that answer correct in your feedback you're sending me. Now, some of you are getting about 800 kgs per meter cubic. I want you guys to revise what you're doing, because 825 divided by 0.917, it's equal to 899.67, so almost 900 kgs per meter cubic. Now, specific weight is equal to what? Is equal to the weight divided by the volume. We already found the weight from the first part of the question here, 8.039 kilonewtons divided by 0.917, and that will give you, so if we use the calculator, 8.093, make sure it's in kilonewtons so you know the units, 917, that will be 8.825, which is rounding to, will be 8.83 kilonewtons per meter cubic, because it's weight divided by volume. The last one, which is dimensionless, the specific gravity for that is the density of it, which the value you found already earlier, 900 kgs per meter cubic, divided by the density of the water. So 900 divided by 1,000, that will give you 0.9, which is the specific gravity. Remember, specific gravity is dimensionless. There's a question, can we use specific weight rho times g? So if you use rho times g, which is 900 times 9.81, you will get 8.829, which is equal, divided by 1,000, which is exactly what we did. So 8.829, which is 8.83. So yes, to answer your question, it's very clearly, yes, you can use W divided by V, or you can use density multiplied by gravity acceleration. Of course, you can use that because both of them, they are correct. They're related to the fluid. If you see there is a relationship between them, volume and volume is constant. Therefore, there is a relationship. You can substitute that in terms of density times gravity acceleration, you get the answer. So for is 803 kilo M. I'm just confused about your units. What's the unit of specific gravity? Specific gravity, no units, is a ratio. So if you look at is the ratio between the density of the substance, the fluid we don't know, to the density of the of water, which is 1,000 kgs per meter cubic. So if you look at the units here for specific gravity, they will cancel each other. So kgs per meter cubic divided by kgs per meter cubic, they will be cancelled. Therefore, it's a ratio. And if you look to the definition for specific gravity, is the ratio of the density of a substance to the density of water, of pure water at 4 degrees Celsius. So it's already defined as a ratio, therefore no units for ratio, dimensionless. Right? So this is part of the session which is introducing you to densities and properties. Now we start maybe the other topic. I will put all those slides, by the way, on Moodle. Now let me open another slide. Okay, second topic. By the way, I'm using different resources, but the one you have on Moodle, they're really good and very good. I can really present a couple of them. So, for example, so this now I'm putting on the share, like the one I'm sharing with you guys, is the lecture notes from Moodle, the one you found. So what we covered, let's go through it by step, so at least you know what we're doing compared to the PowerPoint slides, which is just summarizing things. So we define the mass, we define the volume, we also define the density, we define the specific gravity, or by the way, sometimes we call the specific gravity relative density. That's the other definition for it, when it's relative density or specific gravity. So when we call that, if it's specific gravity density of substance divided by density of water, or sometimes we call it relative density. Two names, don't confuse yourself. So if you hear that, are we going to have this part in the final examination? Yes, there's a question about the principle of fluids. Of course. We haven't done much of fluids yet, it's just basic we touch. We define the specific volume, and we define the specific weight, gamma, which is rho GH, or weight divided by volume. Now, one thing we need to talk is dynamic viscosity. Dynamic viscosity is a measure of fluid's resistance to flow, which is the units for the mu is used for dynamic viscosity, and its units pascals times seconds. Kinematic viscosity is the ratio of dynamic viscosity and density of a fluid. So it's mu divided by density. The units for it, even it's a ratio, but actually there is a unit for it, is meters squared per second. And mu is the Greek symbol for it, like this. We call it nu. This one is mu, this one is nu, so it's different between them. Also, we have a topic which is small surface tension. The free surface of liquids act as perfectly flexible skins or membranes with a constant tension per unit length, called surface tension, sigma. As values are small, the units are normally in millinewtons per meters, or 10 to the power minus 3 newtons per meter squared. Here is telling you surface tension values decreases as the temperature increases. and depends on fluid in contact with the free surface of liquids. Surface tension is constant throughout a liquid surface and acts in the plane of the surface normal to any line in the surface. Here's talking you about more. We did cover the pressure as well. Define the pressure is equal to the force divided by the area. 1 bar is equal 10 to the power 5 Pascal or equals 100 kilopascal. This is a standard number. Atmospheric pressure is 101.325 kilopascal or 101,325 Pascal. So either you introduce it in kilopascal or Pascal. Of course, there are a couple examples here. We did something similar to it in the PowerPoint slides. This is, we introduced Pascal, which showing you that you have a smaller area and you can push liquids here. There is something on Moodle which I'm trying to access to it. It's very nice and we'll go through it. This is just a relationship between the fluids. Now we kind of relationship between fluid pressure and depth or head, which will start very soon. But just I want to show you some other slides. So you know this from a depth. The pressure at any point inside the liquid is equal to the weight of the liquid above the point. The relationship between pressure due to self-weights and depth is given by this equation. So pressure is equal what's rho gh, which rho represents the density, g gravity acceleration, and the h is the depth. So similar to when you're diving, where as soon as you go deeper, you find there is high pressure on you. So that's what we're trying to measure is the depth. We call it hydrostatic pressure, can therefore be expressed in Pascal or as a height as a head pressure, which could be in meters. So the H represent the head or P represent the Pascal. There are a couple examples, but I'll show you something very interesting when we go through it very soon. All right, so all right, if you see this example, the one at the end, because I'm zooming it, I'm hiding the solution, calculate the pressure at a point 18 meters below the surface of the sea. The relative density of sea water is 1.02. 1.02. Now, what's the relative density? Is similar to the specific gravity, the other name for it. So it wants you to calculate the pressure. So if we take this question and bring it to the slides and see how can we work with it. Slides. All right, this looks better. Okay. Calculate the pressure at a point 18 meters below the surface of the sea. The relative density of seawater is 1.02. All right, this is something I'll explain to you the theory behind this. But first of all, I need to sketch something to make it very clearer than even in the notes. So let's say this is the bottom of the sea. Let's make it a bit looks more professional. So let's say this is the bottom of the sea and this is the water here. And let's say there is a distance, this person is about the depth of that. If we put this arrow and we put the dimension, it's 18 meters. All right? And the fluid here, we don't have anything about the fluid. The only thing is giving to us about the fluid is RD. RD, it's equals to what is specific gravity, SG, which is equals to 1.02. All right? So again, if you ask me what are its specific gravity, the different names for it. Some of you start getting the answer. Well done. This is really good. Now, what's going on if we assume this is the surface? I just need a tiny triangle. Okay, let's rotate this one. By the way, when you draw something like this, that's represent for you the sample of this represent this is the level of the water. Okay, now I'm not just trying to solve this question for you guys here. I want you really to pay attention because I want to explain the physics behind this application. It's very important to understand the physics. So the pressure at a point 80 meters below the surface of the sea. So let's assume this is the sea, and we're trying to find all the properties for the sea, okay? This is the sea, and here we want to find everything. Now, if I ask you a question, what is the pressure at the top of the sea? So at this point, what should be the pressure? I put question mark. What's the pressure? Now you say, you could ask me and say, what do you mean? Which pressure? We have two pressures. There is a pressure called atmospheric pressure, and there is P gauge. So I need to be more specific here. So if I call this one is P gauge pressure, okay? So what's the gauge pressure at the top of this one? Okay? What's the pressure at the top of the sea? Can you answer me? If you can, guys, write on the privately message. What's the pressure at this point where I'm looking at? Not visible. Okay. Someone is saying it's not seeing what I'm drawing. Okay. Sorry, guys. I was doing a lot of things. Good. Some of you trying to how to know whether it's in kilopascal or Pascal. Sorry, Michael. I don't really know the things. All right. So let's go back to this question. Calculate the pressure at 0.18 meters below the surface of the sea. The relative density of the sea water is 1.2. So I was sketching, this is the bottom, and it's 18 meters some depth. The sea relative density is equal specific gravity and is equal 1.02. I want to find the P gauge at that point. So can you tell me exactly what's the pressure at this point? I want gauge pressure, not atmospheric pressure. So there is a relationship between the gauge pressure at the surface. Perfect, so I get an answer. Since it's open to the atmosphere, this should read for me 0. 0 pressure, 0. And by the way, kilopascal or Pascal? Kilopascal. We always write 0, let's say it's 0 kilopascal, right? Now, if we want to find the pressure gauge at this point, at that point, whereas the depth is 18, what's the equation? I'll write the formula, equals, I will use the equation editor. So that's equals to, do you remember the equation? Rho G H. So let's try to find what's rho. Now here's a problem. I don't know rho. What's the value for rho? But what I know that the relative density is giving me 1.02. So because as I told you always, I'm a very lazy person, I can write this is straightforward 0.02 multiplied by 1000 multiplied by 9.81. Just wait for me, and then I'll explain to you, and then multiplied by 18 meters. Wait for me, and then I will explain this for you while I'm doing here step by step. So what does mean what I have done here? Now you say, hey, why you represented density by multiplying this together? Because remember from the equations, now since we know it is very standard, I'll write the equations for you. Relative density, RD, or specific gravity, by the way, capital letters, small letters is up to you, no problems. same thing as you know them. It's what? Density of the substance. So we call it density. So if we have rho for S, let's call it S, divided by what? By 1000, which is the standards we know is the density for the water at 4 degrees Celsius. All of this equals to what? Equals to the value is giving to us 1.02. So instead of me doing this process and spending a lot of time on it, I know always if I multiply the value of RD or SG times 1000, which I did here, it will save me the time, because if you rearrange this equation again, what should be equals? You say, for example, you will say rho S is equals to, do it here, so density, just choosing the right one, equals to 1.02 multiplied by 1000. And then you took it there. So that term, if you see here, I replaced it straightforward in that way. So that's exactly what I have done here. And that's me, I'm kind of saving time for myself to just make the process easier. So that's what I'm showing you here. I already done, but very quickly. So 1.02 times the 1000. 1000 represents the density of water at 4 degrees Celsius. 1.02 is the relative density or specific gravity times 9.81. Where it's coming from this equation is the gravity acceleration times 18. So if I do that, what should be the answer? If I multiply 18 times 9.81 times 1000 times 1.02, and that will give me some big number divided by 1000. So what have you got the answer for it, guys? What's the pressure at this point? Do you know, guys, the pressure at this point? 180, perfect. 180 point, my calculator, 11 kilopascal. Let's make sure to change the kilopascal to look more. Nah. Okay, it's not like how we write it like this. So that's how you calculate the pressure at that point. So what's telling you? Remember this when you're diving. When you are at the surface of the sea, there is no pressure at you. There is almost zero pressure. You don't feel any pressure. But when you go and try to dive 118 meters, there is about 180 kilopascal pressure against you. And that's why it's very, very, like not many people can manage that pressure. And that's what we say, divers, they need to train because they're coping with the pressure. Now, what we found in both cases, this is the P gauge pressure. Now you say, why is a P gauge? Because we have P absolute value, an equation to calculate the equation for the total pressure. So what we have, P absolute value equals to what? P gauge plus what? P atmospheric pressure. And you know what's the atmospheric pressure? Atmospheric pressure is the 101.3 kilopascal. So here we write another equation. P atmospheric is equal 101.3 kilopascal. Right? So P absolute value is equal P gauge plus P atmospheric. Since I found it here, so if I say what is the absolute pressure value at the surface of the sea? Now I'll trick you here. Here will be the value is equal 0 plus 101 will be 101.3 kilopascal. You see the difference between them? So this could be read in two ways. Now, if I can say what is the pressure value, absolute value at 18 meters depth will be 180 0.11 kilopascal. Make sure to write the units so no one got confused. And plus 101 kilopascal. So that's the pressure. I'll put it just above it here. You add these together since I have the calculator here. So this one plus 101.3, and this will give you 200 equals 281.4 kilopascal. Just let me organize these equations. It's like messy. So you get them. All right. So what's the takeaway from this? There are two ways to show pressure values. I don't want you guys to confuse yourself with it. This should be absolute, sorry. This should be atmosphere. Just mix my equations. Let me fix them. 101.3 kilopascal. Okay, now that looks better. So if I'm talking about gauge pressure at the surface of the ocean, sea, reservoir, tank, an aquarium, P gauge will read 0 kilopascal at the surface of that, at this point, at the surface. Now, if I say, hey, this is the gauge pressure, what about the absolute pressure? I'll say, oh, okay, for absolute pressure is actually, I need to add the 0, which is following this equation, 0 plus 101.3 kilopascal, so the absolute value is equal, which we could simply say the absolute is equal P atmospheric pressure. It's another way to describe that. Now, if I'm going to depth 18 meters there, so that will be slightly different. What will be the difference? You will get the value we found, which is the P gauge, a 180.11 kilopascal, plus the atmospheric pressure, and that will give you the total absolute value to 281.4 kilopascal. This is the way how you distinguish between gauge pressure and absolute values pressure by using this equation, which I will highlight in yellow. Maybe bigger. All right. So this is very, very, very important for you guys to distinguish between these two values. So that's one of the things I wanted to discuss. Let me go back to the yeah. So that's where it's coming. Let's see the answer. Yes, the answer was 180 kilopascal. But if you've seen, I went further than this because I was trying to show you how can you take into account the absolute value as well. Calculate the headwater. So let's give you now time to try to solve this question then. Let's go back. Right here. Okay. So let's choose another slide. Okay, give you time now. Try to solve A and B for this question, for example. So part A, calculate the head of water corresponding to a pressure of 101 kilopascal. Calculate the corresponding head of mercury. Relative density of mercury is 13.6. And give you time. You don't need to look to the notes, and then you can work it out step by step, and you can see the answer for it together. Any answers for the part A? So part A, I start getting a yeah. So body, perfect. What's PS? Where did you find PS, Michael? Buddy, your answer for part A is correct. Try to find part B. Yeah, sure, no worries. Oh, sorry, I didn't hear you a moment. Yeah, you did write me a comment, PS. What's PS? Where did you get the PS from? Yeah, Parkinder, your answer is correct for part A. Matthew, yes, correct. Buddy, yes, part B is correct. Head of water is 0.103. No, no, Ronnie, need to check the answer. I just wanted to know, why do you need to times by 1,000? 1,000 because the density of water is 1,000. So what's the relationship is telling you? That's always to find that any other fluid densities, we take it with respect to the density of water at 4 degrees Celsius. So the density of water at 4 degrees Celsius is 1,000 kgs per meter cubic. That's where it's coming there, 1,000. All right, let's check the answer for the first one. So again, I will try to solve this step by step. So the equation we say earlier, pressure is equal what? Density rho GH. So it's just the equations we need for that part. So let me split them up. Sorry, please. I can solve it here. All right. So if we use that, so we have the pressure, we need just to rearrange the equation to be something different. So we rearrange this equation by writing it slightly different. So H is equals to what? Equations, H, which is the head pressure, is equals to the pressure, which we had earlier, divided by what? Divided by the remaining of next to H, which is the density times the gravity acceleration. And then you substitute the values. So what do we have? We have 101, sorry, I need to add the friction. So you have 101 times, because it's kilopascal, so I'm changing it to, times 1,000. So that's the 101 kilopascal to pascal, divided by the density. Now calculate the head of water corresponding. So the density of water, we know it is 1,000 times the gravity acceleration, which is 9.81. You solve this together, technically the 1,000 will be cancelled with the 1,000, you'll get an answer of 10.3 meters. So that's for the first part, very easy to solve. Now the second part of this question, calculate the corresponding head of mercury. Relative density of mercury is 13.6. I think we have done this, but in different ways. So we use the same equation here, and let's see, we'll start with it. I don't need B. Okay, so now in this equation, what we have, we need to write the application for it. So what's the number here? So what do we have? We have the pressure 101 times what? The because we need to convert that to 1000. Okay, and then we have, because it's the density, relative density, as I'll write it down, is 13.6 times 1000 times 9.81. And then you solve this, you will get the answer 0.757 meters. That's based on what's showing. So again, the pressure, and here it's relative density multiplied by density of water times the gravity acceleration, and you get that. So is that 1000 there because we need to take into account water? There are two 1000. One is the water, yes, and the other one is to convert kilopascal to pascal. So there are two different things. The one here is, yes, we're converting because we're trying to find, we know it's mercury, but we're trying to find it with respect to multiplying by the density of the water to find the substance for it. All right, so this is really good. Two examples, very basic from your lecture notes. Now, need to go back to the lecture notes you have, so I can talk about a couple of the things here. We saw a couple of examples now. You can do this example, it's straightforward. Now, variation of pressure with depth. This is a very, very important. Pressure varies linearly with depth. So as much as you go deeper, your pressure will increase. Equal pressures on same horizontal plane. So if the pressure at the same level, you will get the same pressure. So what does mean? Let's look at this example. At the top of these points, here and here and here and here, they have zero gauge pressure, or the absolute pressure is equal to atmospheric pressure because it's open to the atmospheric pressure. That's what we call it. Now, if I go a depth of H, all point pressure at A, pressure at B, pressure at C, and pressure at D, they will have the same value. Then you say, why? Because the shape of A doesn't look like the shape of C or D or B. It doesn't matter of the shape. Its only thing is matter is the depth. So that's the depth is important. Now, how can I have different pressures? If I'm trying to find the pressure at this point, yes, that will be a deeper than B, C, and D. Therefore, the pressure at A, if we assume A it was here, then that will be a higher pressure compared to them. So it doesn't matter how it looks like the shape. The most important is pressure varies linearly with the depth. So as much as you are going deeper, you get that pressure is going to the depth related to it. Pressure is a function of depth only. So you can see as much at the top of the surface, you get zero pressure. At the bottom, you will get the highest pressure in this example because that's where is the bottom. So if you try to swim in a swimming pool, you find when you're at the top or the surface of it, you're not getting any pressure. But if you go deeper, deeper, deeper and try to dive, you find the pressure at maybe 3 meters depth or 2.5 meters depth is more, and that's why we call it rho GH. You calculate it, depends on that. It's from the equation. First is related to gravity acceleration because you're going deep. Secondly, is related to the density of the fluid, is water. It's not similar you dive in mercury or different fluids. And H is the depth of it. And it's showing you here a different example how much the pressure goes. So the pressure at the bottom of both containers is the same. It doesn't depend on the volume of the liquid. So it doesn't matter if it was open or a container, it's smaller. No, it's the depth. If H values are the same, then the pressure should be the same. Conditional, you have the same density, the same fluid. Because different fluids, they change the value, and you can try it. Hydrostatic forces on a plane, vertical, immersed surface. I think this topic, we may go to the PowerPoint slides because we can talk about it and then we can get back to it. So again, this is a force due to static and fluids, just a very nice topic. I will explain to you one of the slides. I'll show you this example. This is one of the examples I like about this topic. So this is a cylinder. You have two different fluids. If you look carefully to this cylinder, what do you have? At the bottom, it's water. At the top from it, about 1.5 meters above the water, there is oil. Specific gravity for oil is 0.9. Now, straightforward, you can tell me the density for oil. Can you tell me now the density of the oil? Yes, guys, the pressure at the surface is always the same. What's the density of the oil, guys? The density of the oil. When its specific gravity is given 0.9, what's the density? And make sure to write the units. Yes, Sagar, correct. Yes, perfect, Papinder. And that's the answer it should be. So it's just now, it's straightforward. It's just 0.9 times 1,000, and you get that number. So that will save you always the time. And you need to specify the units, kgs per meter cubic. So the pressure in the water at the bottom of the drum is uniform across the entire area of the entire area, because it's a horizontal plane in a fluid's at rest. So we know that the diameter of that cylinder is 3 meters. The diameter for it. So now, if I want to confuse you guys, I always do this in this kind of questions. Let's say I have a cylindrical shape similar to this one. So let's say that the shape, I change it from that way. We say we have the same height, the same depth, and the shape is changed to that direction. And let's say this is where's the fluid. So we put it at the same level. And also we separate the fluids. So let's say we have water and oil at the same level. So if I change the shape, do you think the pressure at the bottom of the cylinder is it the same to this example? Taking into consideration the diameter is 3 millimeters or not? So if you're calculating force, yes, the force values are maybe different, because force is equal watts, pressure multiplied by area. But pressure in the bottom is the more? Yes, more. But I'm comparing. Do you think this scenario and this scenario, they will have different pressures? So if I say I want to find the pressure here, let's call it P1, and the same thing, Control C, and call it here P2. So do you think P2 and P1, they will have the same different values, even I have changed the diameter here? Do you think the pressure is different? And with taking into consideration, here is oil. So I will put here Control C. So here is water. And on top of that water is oil. Control C, Control V, oil. And the same density, it's 900 of RD 0.9. I know I changed the diameter. See, I'm tricky. I'm asking about pressure. Diameter is changed. See, that one is 3 meters. This one is slightly different. And even at the top is different. So the question is, but what I kept the same, so make sure that I kept that distance from here to there is the same, which is, let's put it here, 3.9 meters. A bit crowded on this side, so let's bring it this side and make this one be more. So now the question I'm bringing this question again to you guys to think about it for discussion. If I change the dimensions, I kept the depth as 3.9. 3.9 is 2.4 plus 1.5, so that's will give you 9 and 3.9. It's still the same oil and water. Nothing is changed. The diameter at the bottom is changed, of course. Bottom and top, nothing is different. My question is P1 at the bottom here is same as P2 at this cylinder? That's the question I want you to answer. Michael, I think, is the same. Who agrees with Michael? P1 should be equal P2 because it's the same depth. Perfect, Matthew. So you see the trick is here. Yes, they are the same. Now, if I tell you, now if I say, okay, let's trick you again. Control C, Control V. What about if I say, is the F1 equals to F2? Now what you say, so the force at that point, is it equal to the force at this point? Think about it. I think is different. So the force, someone is using difference. Good reason, Michael, and good reason, Matthew as well. Yeah, good reason. So yeah. So yes, of course. So let's try sum up here and to sum up this example. So what we say, P1 is equal to P2 because same fluids and same depth. Now, F1 is not equal. How can I get is not equal from the equation? That's will be challenging. Do we have non-equal? Yeah, I can't find the non-equal. Yeah, I found it. Non-equal F2 because area 1, it's not equal to area 2. That's very simple. So what's telling you? Yes, you may get the pressure is equal, but definitely the areas are not the same. Therefore, when you calculate the force is equal what? Pressures multiplied by the area. And that's what give you that's explanation for it. So don't be tricked by the shape. When we calculate pressure, it's slightly different from force. And that's why we're trying to tell you to prepare you for the next session. I think we're done for today. It's really good. So if you have any questions, I will answer now. I open for you guys, so you can write me on the chat so I can answer any questions you have, guys. And I'm still recording the session, so as soon as we finish, I will stop recording it. But if you have any questions you want me to go through, I'm very happy to answer as much as you have questions. So I'm waiting for you guys to write me on the chat. Do you guys have any questions? Yeah. Okay. How to know the units? Because I'm confused, like whether it's Pascal or kilopascal. Okay. It depends on the number. So if you're solving it in meters, in meters square, in anything the normal standard units, then you always use Pascal. And then when you get a big number, like 100,000 something, you divide it by 1,000, and then you make it 101 point something kilopascal. So always depends on the standard unit you're using. So if your force was in newtons or was giving to you 10,000 kilonewtons, so you need to convert 10,000 kilonewtons to newtons. And if the area was given in millimeters square, you need to convert it to meters square, and then you get the answer in Pascal, and then you divide it by 1,000 to change it to kilopascal, or 1 million to change it to megapascal. And depends on you. Any other questions, guys? Any other questions? How do you find the pressure at that depth? The pressure at that depth, that's a good question. So basically, you move from this point to this point is rho GH using the 2.4 meters and density 900s, gravity acceleration, you find the pressure here. Now that pressure is adding on the pressure of the water, so it will be that pressure you find plus the depth. So technically, the pressure at point 1 or point 2, or whatever one of them, I'll write it down for you. Bring it here. We'll explain it in more details next week. So it would be 900s times 9.81 times the edge, which is 2.4 plus. So that's all pressure stopped till where the oil finish. Now plus what? You have 1000 is the density for water. Sorry. Times 9.81 gravity acceleration times the 1.5 meters the depth. So that's the total pressure at the end. Make sure to use the right brackets. Don't want you to confuse these equations, so I will use square brackets. And you add these two terms together after multiplying them, and then you get the total pressure at the wall of the cylinder at this point. I hope that will answer your question, Saga. And the pressure from both fluids. How do you find the pressure? Yeah, that's how you find it. So pressure from both fluids. And then when you find the pressure, you will get the cross-sectional area for the 3 pi over 4 3 square multiplied by that P1. You get the force at that spot. Very easy. But we will do this next time when we meet. So remember, Monday we don't have a class, is Queen's birthday holiday, public holiday, and Friday you have the project presentation. So I want you to prepare for that, and then on Monday, not next week, the week after, I will give you the date, the exact date. The Monday, so we'll lose that 4th of June. So I will see you 11th of June with the fluid mechanics. So we'll finish the course and then we start hopefully tutorials with the topics related to the entire course you have covered in this course. All right, so by this, I will conclude this session, guys. I will stop the recording and